Hello, everyone. This is Universum, the place where you learn about the entire universe, how it began, and how it will end. Today, we are going to be talking about how it will end, and it'll mark the end of the basics of astronomy. Then move on to our next unit, as we know it. As Carl Sagan has said once, it is said that astronomy is a humbling and character-building experience. There is no better demonstration of the folly human can cease, as I've said in my first video. And one thing that I would like to demonstrate to you guys is the nature of dark matter and dark energy. So as I explained in my last video, well, my last two videos actually, they were part 1 and part 2 of the videos, in order to make them a little bit shorter. Now, one thing that you guys noticed is the way dark matter and dark energy work and how they're linked up to time dilation. Now, today we're going to actually exploit what they are in a more simplified manner, in case some of you guys struggled a little bit on that. So, just so you know, just get a little perspective on how much dark matter and dark energy is in the universe. There is about 90% dark matter and dark energy combined in the universe. Well, the other 10% would be exotic matter and ordinary matter they see day to day around you. They might be wondering and asking, how is this possible? How is it that our universe is made out of all this stuff that we see around us? I mean, we can see all of these different types of matters around us. We could see gold, as we can see for our imaginary values. We can see silver, as seen in glorious beauty. We can even see copper, like seen in shells of bullets. There's graphite, or otherwise known as ionized carbon, inside of our pencils. If you actually sharpen it, you actually can make it, excited. You can excite the electrons and put them into a higher energy state, since due to all the electrons being in a zero position. The zero position basically means that they're bouncing around between different energy states. The farther they are away from the atom, the more unstable they are. Although everything in this universe wants to be stable, so then it'll release a little bit of radiation in the process. Although when people hear radiation, they think that, it's something bad's going to happen. When really, radiation simply just means to give off. Radiate, meaning give off, and then, ation basically just is a root of it. Basically, it just means that it's a topic. Anyhow, there also are different types of elements that we can see that we can use for many different types of practicalities. Like, for instance, the tungsten in the space pen. And many, many other applications, as we could see. But yet, there's so much that we don't know. Something dark, called dark matter and dark energy. Now, dark matter basically could be something that could keep the galaxies together while pushing them outwards. Basically, it's a radial force. So, let's say if you were pushing someone outwards with your hands, and then there was someone pushing inwards, that'd be gravity. That'd be squashing you. That'd be the weak force also. Then that would create a counteractive force. And then what happened next is then it would create a stable equilibrium between them and then keep the galaxies together. Without dark matter or dark energy, you have no galaxies. You simply just have a careening path of stars flying everywhere where no planets can form. I know, it's insane. Then there is dark energy. Dark energy is what speeds up the expansion of the universe, and it's even more strange than we think. Now, although there are many candidates for what dark matter and dark energy could be. Now, honestly, in my opinion, I don't think that dark matter or dark energy is not necessarily dark, but I think that it just doesn't have any influence in the Higgs field or the gravitational force, and I think that it has some other force that possibly could be counteracting with it, and that we aren't able to detect yet. Our instruments just can't detect them yet because our instruments aren't that sufficient. Maybe the James Webb telescope will shine a little bit of light on this dark topic. The one thing that we also had to start studying about is the nature of the expanding universe. So the expanding universe, as we know it, expanding. It's a radial. Although I don't think that our universe is I don't really think that it's just a giant encased shell and there's nothing outside of it. I think that our universe possibly is some sort of other shape that we can't necessarily define. I think it's more of like the flat world hypothesis. The flat world hypothesis basically no, it's not flat Earth. Just letting it out. Disclaimer. So the flat world hypothesis basically means that there was this science fiction author that was in the 1920s, and he made this book. It's called Flatland. Well, actually, it's a perfect candidate for everything as we can see, everything that we know of. So let's say this equation that I just wrote. I know it's a little bit jinked up, but as you see this equation, it is two-dimensional, although it still has little height, but let's just ignore that for the sake of this argument. They have width, they have length, but they have absolutely no height whatsoever. Or at least, as far as we could tell, at least. I mean, yeah. Now, they can move forward, backward, and left, right, but they cannot move up, down, due to they're trapped in their dimension. Although, imagine if we were to curve a space. That's like, what happens if ultimately what they perceive is only what they think they see, when really they are on a parabolic space. They are in a 3D world instead of a 2D world. That's what I think about our universe. I think that we really are in a 4-dimensional space when we really are just trapped in the third dimension. Maybe it's just our relativistic perception. Who knows? Nobody knows yet. All right. So now, let's go. Now, let me just tell you why I think this is full. First, we have to talk about Euclidean and non-Euclidean geometry. There are a few postulates that this ancient Greek mathematician made called Euclid. Now, Euclid was a brilliant mathematician and astronomer. So what he did is that he made the Euclidean postulates. Now, these are really, really easy. You learn these in high school. Now, I know I'm not in high school yet, but I'm learning high school level classes. Anyways, so the first postulate would mean any 2 points only have one way to one another. They can't do any other way. Now, many people argue with this and like, wait, can you just go this way or that way? No. They both are in a superpositionized state. They go exactly at the exact same time. They are relative to one another. Another thing is, all angles of a triangle make up 180 degrees. When, in a non-Euclidean space, they make up 270. That is pretty crazy when you think about it. Another thing is that two parallel lines cannot meet. And then another one would be all angles of a square are right angles. And the last one would be that they all are encoded on a two-dimensional surface. But what happens if these are all wrong? For any of you guys who are in high school, this would seem insane. This is non-Euclidean. And this is why I think that our universe cannot be a sphere. Since this means that, so let's say we were to cast some rays around. Let's say, I know we live on a sphere, but our perception is not a sphere. If our perception was a sphere, then it would be a lot different. But our universe can't be a sphere. Since let's try to do a little bit of experiment. So here, this would be a light source right here. There are photons that come out of it, then get bounced off the object, and then it transfers its information into that object that it does the photons into. Now, if it was non-Euclidean, let's say a spherical space or a hyperbolic space, although it turns out spherical spaces are even weirder than hyperbolic spaces. And the hyperbolics are harder to visualize. Like, for instance, I'll give you guys an example of a hyperbolic space. Now, so first let's give you an example of a spherical space. Of course, this plasma ball right here. Now, honestly, it's not really that different, but let's say your perception was that. This is that the light waves that'd be traveling. Well, they would go all around. They would appear upside down like a reverse refraction. It would seem insane. This means that farther away objects would seem huge and upside down, while closer objects would look smaller and normalized. Well, in a hyperbolic space, simply your light waves that are traveling from an object, they go all around the world and then back into your eye. This gives you a bigger curvature of any object that you're on, and it basically just makes it look like a exaggerated Euclidean space, due to it being hyperbolic, of course. But that's why this crazy argument tells me that our universe cannot be a sphere. Since think about what we'd see. Literally. So let's say that poster back there. What you would see from that poster is that, well, it would appear upside down, and it would appear huge. It would take up my entire ceiling. Yeah. That's why I still think that we are not living in a spherical universe. I think that we live in some sort of other higher dimensional universe, and then our perception tells us that it is third dimensional. Now, let's go look into the future a little bit. So, what happens after our sun dies? Well, some of you guys may think that, the sun's gonna die in a giant explosion, when really our sun's not that type of star. It's a yellow dwarf star, and it is currently in its main sequence process, which means that, well, it is a smaller type of star. It's one of the more common types. And it just so happens to give life to you and me. It gives about 99.998% of all the energy on this entire planet. But anyhow, now let's go for the larger stars. Now, even though our sun will grow to a red giant, it won't grow to a red super or even hyper giant. Those big behemoths that can get up to the Saturn system. Now, one thing that we also have to look at is, well, first of all, those stars will be gone in no time at all. But then let's look at our sun. So all stars must go at some point. The universe will then fade. Yes, and as the universe goes throughout, entropy will take over, and then the Higgs field, which is what takes charge of all of the particles' processes. In fact, it's the only boson that's not a gauge boson. Yes, and the other four types of bosons that are gauge bosons would be gluons, which hold quarks together by a strong force, and then there'd be X, Y, and Z bosons, which contribute to the weak force a little bit. Although the Higgs field is mostly what contributes to the Higgs field. Now, the Higgs boson, as entropy takes over, it'll demand more stable and more stable states. This means stars will get smaller and smaller and smaller, until basically all you'll get are just Jupiter-sized planets. And that's it. That's the end of the universe's story. Or at least we think it is. Now, one thing that we also have to get to the nature of is a little bit more of how our universe works after this stage. So let's say the longest stars that will exist are white dwarfs. And any stars that will be created, well, these won't really create stars, but they still will create gas clouds. By the way, just letting you know as a little disclaimer, at this point, this is when all the galaxies had disintegrated. They're all gone. So don't expect any galaxies at this point. Anyhow, so there are two ways that stars can be created at this time. When two Jupiter-sized planets, or brown dwarfs that are a little bit heavier, when they fuse deuterium into tritium into helium, and then into one neutron to start off the chain reaction again. All of this neutron is traveling extremely slowly. So let's say if two brown dwarfs, they would collide with one another, since they'd create a bigger, more denser gas cloud. It'd create a star, due to it being a little bit more dense. Another way for them to be created would be when two neutron stars are going against one another. Now, obviously, these are the old, cold neutron stars that have lasted billions of years. As gravitational waves influence them, they get shorter and shorter and shorter until ultimately they collide with one another in a kilonova explosion. What a magnificent and horrifying scene it would be. Yes, it would be beautiful, and also in the future episodes, we also will be talking about strange matter and strangelets, and how when a kilonova explosion happens between two neutron stars, they may collide together, and then they could break this weird substance that's called nuclear pasta. And then underneath it, well, if the two neutron stars were quark stars, then they could release strange matter, which basically just ultra condensed quarks, which are ultra stable, and everything else in the universe, due to them being of a higher entropy state, they then would want to become one of them. Pretty crazy, eh? So now, as we go throughout the universe, even the white dwarfs will die. And white dwarfs can live up to a billion, a trillion, billion, 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 billion years. Longer than any other star will ever exist. And when the first white dwarf turns into the first black dwarf. Black dwarfs are stars that they basically are just the cold types of white dwarfs. They are so condensed that they are nearly 100 times the mass of our sun, but yet only about 3/4 the size of the Earth. Pretty crazy. They also are so dark that they're merely invisible. So cold that they're still big enough to kill you. So cold that it's almost at 0 Kelvin. And in case you guys didn't notice, a Kelvin is extremely cold. That, in fact, when Lord Kelvin actually came along, he actually was the one who discovered it. And now all astronomers and physicists call him Lord Kelvin now, due to making major contributions to astronomy and how it works. But even the black dwarfs might die in this process that's called proton decay. Since as higher entropy states get higher, the Higgs field will demand more and more stable particles, and heavier ones too. So that in the end, the proton will get knocked out of the scene. Then it will decay into a neutron. And then, let's say if there was a helium-2 nucleus, due to opposites attracting, they attract one another due to the strong force. But because now they're of the exact same charge now, they all just fly apart. This means that over a very long time, these black dwarfs would decay into nothing, literally. All they leave behind is a few sea of photons behind. And then, but if the proton does not decay, it may turn into it. Now these helium nuclei, they may fuse together over an extremely short amount of time, guided by the strong force. It's an unspeakable amount of time. To give a little perspective, it's higher than Graham's number. In the end, they'll turn to iron spheres. These iron spheres will travel lonely in the dark abyss of space. No stars to look at in the night sky anymore. Nothing to look out at. There'll be no photons that will hit your eyes, so everywhere in every direction will look dark. You wouldn't be able to see yourself if you were in this awful abyss of interstellar space. This era is called the degenerate era, and this is when we get down to black holes. These black holes, now, basically, there still will be sort of galaxies, but these, as many astronomers call them, they call them zombie galaxies. Galaxies with a giant black hole in the center, and then with smaller black holes accreting around it, feeding into its accretion disk, and panging on the universe, making it louder and louder and louder. But yet, in a sense, it's sort of beautiful. When you think about it, when you look at the universe, when you look at this panging, the little gravitational waves detected by the LIGO detector in Washington, it's sort of like a cosmic symphony. The essence of the cosmos. Like, think about it. in the form of gravitational waves and radiating, followed by the laws of relativity, as Einstein has said in the 1920s. Then the black holes even start dying at this point. Yes, any object, if proton decay is real, well, then the proton, well, the fundamentals of building blocks talk matter would simultaneously fall apart due to thermal equilibrium and entropy. But also, this means that even the black holes will start dying, not only because of this, but because of something that is extremely newly discovered: Hawking radiation. Now, Hawking radiation now many people mistake Hawking radiation for coming directly from the black hole itself, and really that's not true. No, what really is that so quantum fluctuations is what makes, or at least as we could think it does, they're what make the so-called dark matter and dark energy. Well, as we look at them, we start to see that. Anyhow, so we also just start to see that these black holes start irradiating away, now not necessarily from them, but in the form of quantum fluctuation. So when a particle and an antiparticle collide with one another, well, they of course release a little radiation in the process, making the so-called dark matter and dark energy. But while in the presence of a black hole, one of these pairs that are entangled one another in a form of quantum entanglement. Now, I actually have a little bit of a theory on this, which basically states that, well, I base it mostly on Feynman diagrams, which we will explain a little bit later on. Anyhow, so then these two entangled particles, due to one of them being sucked into the black hole, the other one will still be entangled with it, but not necessarily. It's in a meta-entangled state, leaving the other one stranded without a particle to annihilate. This particle then converts itself from an entangled superpositionized particle into a form of radiation coming away from the black hole. Then, as the black holes get older, this process speeds up and speeds up and speeds up until ultimately the black holes themselves evaporate and explode in an enormous explosion until the end, when the last black hole dies, about 10 to the power of, it's almost a Google, plex. When the last supermassive black hole dies, it'll bathe the universe in the last light possible, as seen in almost like a little firecracker explosion. Then it releases its radiation in the process, and then dies. This is Universum, and thank you so much for watching my channel. Goodbye, everyone.